DigiWorld, exactly, this is the correct name. It's a special strategic program on our university that helps us and support scientists and to communicate with other scientists all around the world. So this workshop will be also financed from this program, and they also help us to support with recording and transmitting this workshop for over world. I think that that's it. So
thank you. So we now move to the presentations. So just I think you have the program, and the coffee break will be upstairs. Okay, just one product, you go up the steps. I'll go with a very small group. And then we start with the first round of presentations, and Dr. Julia will chair that session.
Okay, so each of our welcome guests, welcome our speakers especially. Each of the speakers got half an hour to present their talk. After each talk, we have a short discussion, and I also, if you have any question also from the guys that they are on Teams, please write the question on the Teams chat. It will be easier because we have small technical problems with the speakers here. So it will be easier if you guys can write your question on the chat. So we start with the first presentation. So we are welcome Julius Schöning from University of Applied Science Osnabrück from Germany, and he will talk about AI in the loop, HMI, HMC with transparent AI algorithm. So one moment, I only share your presentation.
Thank you for the kind introduction, Arthur. So I will talk about some work some students did, I did myself, as well as some ideas since I'm quite new in academia. So I'm back in academia since 2 years, and before that I was in industry, and there I were focusing on autonomous driving vehicles as a system architect. And so, yeah, I started with Corona and did a lot of teaching during Corona on the online side session. And so research is somehow neglected. However, we will start as the normal lecture with a comic, and read yourself. So sometimes it's important to really agree that we do artificial neural networks and not neural networks. So I'm from, I do have a PhD in cognitive science, and oftentimes we talk about, let's train a neural network, and no one recognizes whether or not this is biological or artificial. And here I will talk about artificial neural network and how artificial neural network with mensch-computer interaction might be improved to be applicable in the next 2 years for certain tasks. And how we can do so, we need to have a look what is applied AI in the nutshell. So when you go to the industry, you will see this process. This process is starting by having data, having an idea, and this data and this idea is then put through a data analyst, and this data analyst, he or she, say, okay, this is our data, and we take this selection of the data, and then we create a data set. Usually, if you work with real-world, non-academic data, this is important to clear your data set. Because academic data is so nice to process. Everything is fine. Everything has the correct information, the correct data, etc., etc. And when you work with real-world data, you need a lot of data set cleaning, as well as to transform the data set in an appropriated format. And then you start the selection of the AI. You decide yourself whether or not you need a CNN or an RCN or some classical machine learning like a support vector machine. So I personally really love the old-fashioned methods because usually deep neural networks are waste of energy, waste of processing time for simple tasks in real-world factories. However, the buzzword AI is so common that every company try to have a deep neural network doing some things, and these things usually can be done within simpler network. And then, of course, we do the training of the AI, and the last step that we have the AI within our application, and the AI then solve a specific task. In theory, this is a straight line development. So in theory, you started over here and you will come back. As we all know, usually we do have the selection, the training, as well as the application of AI. We need a lot of evaluation, and this evaluation then is time consuming, costs a lot of energy, especially when you have to train and retrain your neural network again and again. And of course, if you do think on the monetary content, it wastes a lot of time. So this is the reality. And by looking to the reality, we see, so please neglect the green boxes. I forgot to, they will be important later on. So usually you do have a human-machine interface by selecting the data. You have a human-machine interface by the data analysis. You do have a human-machine interface by the data set cleaning, as well as a human-machine interface for the evaluation. For the evaluation, of course, we do have some matrix, we do have some graphs, as we know from TensorBoard or other things. For the data set clearing, usually we going through the data set and try to find anomalies. For the selection, we have some supporting tools for selecting the data set, so on. However, usually or currently, we do not use human-machine interaction during the selection of the artificial neural network. We do not use human-machine interaction during the training of an artificial neural network, and we do not use human-machine interaction while a neural network is applied. And here I bring, for all three aspects, a possible solution and a possible research paper with me for having some idea how a human-machine interface for these three steps might look like. And the first question we asking us, how we can interactive select the AI architecture, or how deep should I go, or should I go deeper with my neural network? And therefore, we are at the selection of the AI, and we're asking ourselves, does deeper AI models provide better results? So for the task of image classification, right now we are talking about ResNet 50, ResNet 101, and even deeper. So is this really necessary to have such a deep network to detect whether the rose is red or yellow? Or is this network a good choice? And usually what you do, usually you have both architectures available, you have a high performance computing grid, and you compute both networks, and then you have your matrices and evaluate your matrices. However, this is a trend to have deeper and deeper networks. So these are the number of parameters you need to train. And these are the networks starting by the inception V2 in 2015 and going up to the efficient net L2 in 2020 with, I think the multiplied by 100 times more parameters needed for the efficient net L2. And does it really provide better result? The claim of everyone is the depth of the model is related to the size of the data set. So as deeper my neural network gets, so as more parameters in my neural networks will be there, as bigger must be my training data set. This is important to recognize because if I have a small data set, then only a few neurals can be used to be the general solution to ensure that the neural network does not memorize every image in this neural network. So if I do have a million or a high number of parameters, then I need a big data set to ensure that the neural network do not recognize all image. Of course, data augmentation is an important term in this area, because if my artificial neural network has a big bunch of parameters, I can artificially increase my input data by data augmentation. However, this is the current claim. And also a current claim is that the result of the AI will be better if I have more parameters. So this is the usual claim. However, this claim is, in our opinion, not valid. So this were our working hypothesis, that a deeper network doesn't provide better results, as well as the efficiency of each layer. So usually the efficiency of each layer, what is the best amount of the efficiency? So when is a neural network efficient? And therefore we go in our results, and then we see, okay, there is a curve, there is a peak, and then the peak drops again. And also the efficiency here drops again, and we see there is somehow a point where we can say, okay, the number of neural networks, of layers in the neural network is important. I forgot to mention the x-axis is the amount of layers in the neural network. So here with only 1 or 2 hidden layers, and then with n hidden layers. And we did this, or we investigate this on convolutional neural networks. And with a component-wise analysis, we find out that there is point at the layers where the layers saturate, so that the layers do not provide more information to the learning of the classification task. That means that the first layers until here are important for the neural network to solve the task. And after this point, after this situation point, the other layers do not provide significant information to the network. We did this with some eigenvalue calculation, and we proved this more or less by try and error, and later on mathematically, that we do have a drop in the accuracy. So we can predict at which point the layers of a neural network become unpredictable. So this is some finding. And this means if I do have image classification, this is our image. And by having these eigenvalues, as well as by having these receptive fields that we use to compute this saturation graph, so we use their eigenvalues as well as receptive fields, we will find a border layer where this border layer is this point, and behind this border layer we do not have productive layers anymore. And with this information we can, in the option 1, remove efficient layers, or we can make efficient layer and unproductive layers efficient again, for example, by increasing the image size. We programmed a toolbox for this. This is a free available Python toolbox for the receptive field analysis, and this is this can be used in PyTorch as well as in TensorFlow. And the important thing is that we now can test our architectures before training this, and this is how it looks like. This is our output. This is our first user interface, and with our receptive field analysis toolbox, we see every yellowish layer, it's possible in productive, and every red layer, it's an unproductive layer. And by removing all this red layer, we have a new modified architecture of our neural network. And this is done with our toolbox with no training. So this can be done before training, and this saves time, money, as well as energy. And does this have any advantage? We show that by having this on ResNet 18, apply this toolbox on ResNet 18, we can reduce the amount of flops needed for the training with a little drop of accuracy. We can also optimize this network to the hybrid version where the amount of flops during training is a little bit higher. However, the accuracy is better than the original ResNet, as well as here the best quality, the calculation in flops is higher and the accuracy is higher as well. By looking to the number of trainable parameter, by removing unproductive layer, we see that the amount of parameters went down. So the amount of parameters within the network that we needed to train went down. And if the amount of parameters we needed to train went down, each image or the neural network can generalize better on each image. And this can also be seen for other networks. So we did this with a lot of networks, and this is the first option. By a good visualization, the developer, he or she, can easily see which layers are unproductive and then find the optimal network for this optimization. So HMI for selecting a neural network is quite important in our opinion. The second option that we can do with our receptive field analysis toolbox is to define the input image size needed for a specific neural network, ensuring that all layers are productive. And here we see the correlation between the input image size and the productiveness of a neural network. So if the input image is too small, we have unproductive layer due to the receptive field in the convolutional neural network. If we have an image size that fits between the minimum and the maximum input image size, we do have no unproductive layer, as well as here. And if this image is too big, we will miss some important features. For example, here the bottom of the rows or the top of the rows are then not longer covered by the convolutional neural network, and we will lose this information. And therefore, we came up with a table, and this table are based on the existing neural networks, the assumptions, not the assumptions, the best input image sizes the researcher or the developer should use. So, for example, if you want to use the VGG 11, you should have input images 150 by 150 pixel. If you have a multipath network, for example, like ResNet 101, the smallest image size feasible for the network without unproductive layers are 69 by 69, and the biggest size are 971 by 971. And so you can think beforehand, before putting a big image through a neural network or images through training a neural network, which is the size or the possible size. So these are things we can do by selecting the neural network. Then something, it was a funny idea, and this is only in a side work. So one idea is, can we smell the gradient during training? So by having a high performance computer cluster, you usually will look every hour to your graph, or every day how this graph is developing, how the gradient is developing, and usually you will see the results later on. But this might be a waste of energy when something went terribly wrong, you didn't look up it, and then you waste energy. And therefore we asked participants how one can connect smells with the mood. So what smell is positive, what smell is negative. And then in the first try, we try to have the server states in connection with a smell. So if everything is fine on the server, we have a hot apple pie in the office. If something went wrong on the server, we have black pepper in the office. If something went terribly wrong, then you smell gunpowder. And we did this with 10 participants, and here you see it somehow works with these 10 participants. However, this is an early idea. This is the device, this is the olfactory output device, and now the idea is that that we might be capable to smell this training curves, and a student group of mine try to have this gradient of 0 with garden mint, with orange, and negative gradients with gunpowder. However, the first studies show that no one can draw diagram by only smelling this diagram. But yeah, it's only one idea for covering this part while learning. And the other thing is AI in the loop. This is the part in the application. This is the part where we have already trained AI in a certain application, and usually the old-fashioned user in the loop paradigm is we do have a target value, we do have data, we do have a human or an expert, and this human and an expert fused all the values and controlled then the system, and then we go in this control loop. The idea, or the perfect idea of machine learning, is having AI or machine learning within the loop, so as a complete substitute of a user. This works quite good for certain domains. However, currently, and in my opinion, in the next 10 years, AI won't be 100% explainable, AI won't be 100% accurate, and AI won't be reliable on rare events. So by talking to Tesla right now, white truck is not longer a rare event, so it happens. However, how to solve this? By having AI in safety critical systems. And now I try to have the paradigm AI in the loop. So we do have an AI or machine learning algorithm in the loop, but if the AI and the machine learning algorithm isn't sure, then the AI and the machine learning algorithm ask a domain expert, ask a user, and he or she then give a bit of advice, give feedback, or is fail-safe. So the fail-safe, for example, for the autonomous driving. And why I came up with this idea, or why I like to promote this idea. So this is not completely new. This is not my idea, but I like to promote the idea, because by looking on the development, so we are here today, and the availability to the market of full automation is, in my opinion, +2 or +3 decades. And the AI-based expert systems are already available. And with AI in the loop, we can have AI available also in safety critical domains within the next 5 up to 10 years. And then, for example, farmers can use AI to optimize their crop rotation and to optimize the use of fertilizer, to optimize the use of water. And so there is someone in the loop, and the AI will help optimizing the farmer for this thing. So we applied this already in the domain of farming, because we have a lot of farms around our university. And now I will come to the last slide, some marketing slide. So yeah, I'm quite new as a professor at the University of Applied Science. So right now with some colleagues, we applied for national or international funding grants. So this is also the reason why Arthur, Bipin, Milena and myself do research on cognitive science enhancement, and therefore we ask ourselves how we can improve the sense of a bicycle driver, for example, that he or she knew when a truck came from behind. So this is right now only a travel grant, but we hopefully will get something else in the future. Then we at our university have engineering projects, and this engineering projects is 1 semester long, and this is quite practical. And there is always a partner in this project, and right now this is always a company, but it can also be a university, etc., etc. And the rest I do not need to mention. So we make seminars, hackathons, joint theses, and Erasmus is also possible. And this is my last slide, and I'm in the time.